Hello, everybody. Welcome back from winter break. It is currently Friday during winter break, and it's freezing outside. I am wearing about 5 layers of clothing. Mr. Link will not be bringing you the play posit for this particular little unit, so you're going to be listening to the dulcet tones of my voice for this. Okay, so this video covers a few different topics, a couple I don't want to call them random, but a couple different theorems that come up on the AP sometimes that all kind of fit together with the idea of continuity and differentiability. So before we jump into it, we are going to review some definitions. So a function f of x is continuous at a point x equals c if, and I'll give you a second to put an answer into play posit here. This is review. Okay, so if the limit as x approaches c from the right of f of x is equal to the limit as x approaches c from the left of f of x, and that is equal to f of c. So this is the definition we saw earlier in the year. A function is continuous at a point if the y values approach the same value from the left and right, and when you actually arrive at this point, see the output of the function is actually the same point that the two sides were approaching. So, you know, this function is continuous at this point, c, because as we approach from the left, we're approaching the same y value. As we approach from the right, we're approaching the same y value. And when we get to c, the actual y value of the function at c itself is the same as the value we were approaching. Okay, so a function f of x is continuous everywhere if this is true for for all values of c. So if a function passes the test in part A here, for every possible value of c, then we would say that the function is continuous everywhere. So some types of functions that are continuous everywhere. This is going to be important later on. So polynomials, so that includes lines and quadratics, and higher order polynomials. They are continuous everywhere. They don't have any discontinuities. Sine and cosine. Not tangent, but sine and cosine. And then exponential functions. There are some functions that are continuous but not necessarily everywhere. So some functions that might be continuous almost everywhere would be rational functions. So rational functions will be continuous everywhere except where they have a whole or vertical asymptote. So if you're looking at a certain interval and there are no holes or asymptotes in that interval, then the function could be continuous in there. And that goes for any function that has a vertical asymptote. Tangent is not continuous everywhere, but it is continuous on some smaller intervals where it doesn't have vertical asymptotes, yada, yada, yada. So basically you're just trying to be careful about holes in vertical asymptotes. Things like a square root function or a log function, those are continuous everywhere where they're defined. So a square root or any even root function is not defined when the input is less than 0. And log function is not defined when x is less than 0. You can't take log of a negative number. But as long as x is positive, then it's continuous everywhere. Okay. Let's move on to differentiability. What just happened? Oh, there we go. Might be. Okay, so a function f of x is differentiable at a point x equals c. I'll give you a second to go ahead and put this in play pause it. Okay, so a function is differentiable at a point x equals c if it's continuous there. So that's a function has to be continuous at a point in order to be differentiable. But then in addition, the average rate of change on both sides of that point have to be approaching the same value. So this means, approach, okay, I can spell. So some examples of a function that's not differentiable. Famous one is the absolute value function, because at this point, the average rate of change as we're approaching from the left is negative, and then as we're approaching from the right, the average rate of change is positive. So they definitely are not the same average rate of change on either side. Other problematic behaviors are cusps, things where there's a sharp turn. If a function has a sharp turn, then it's not differentiable there. That comes up with some piecewise functions. We'll see that in a minute. But anyway, so some functions that are differentiable everywhere. So a function is differentiable everywhere if these conditions are true for any value of x. So part A is true. So if we are told f prime is continuous, so notice here this is the derivative. So if we're told that the derivative of a function is continuous, that means that the original function f of x is differentiable everywhere. Oops. If we're told f double prime is continuous, then that means that both f of x and its derivative are all differentiable everywhere. So that the reason we need to know that is sometimes in a problem, it will tell you you have some function f double prime is continuous, and then in the problem you're going to want to show that f is continuous and differentiable. And the way you're going to show that is say, oh, well, in the problem you told me that f double prime is continuous, which means that f has to be continuous and differentiable as well. The reason that the continuity of derivatives matters is if we take a look, let's take a look at this absolute value function here, right? So if we were to graph the derivative of this absolute value function, to the left of this point, the derivative would be negative and constant, and then to the right of this point, the derivative would suddenly switch to being that same number but positive. So you get a discontinuity here. So anytime a function f has a sharp turn, that means that its derivative will be discontinuous. There'll be a gap in between somewhere. Same thing with a cusp like this. You would end up having a gap, a discontinuity in the derivative. Excuse me. If we're told a function f of x is twice differentiable, so this comes up a lot in problems, that just means that it means the same thing as if we're told f double prime is continuous. It means that both f of x and f prime are differentiable. So it just means that your original function is smooth. It doesn't have any sharp turns or cusps or anything like that. Okay. I don't know why it keeps. Okay. Okay, so I already drew some examples of this. Absolute value. This is continuous everywhere. You can draw it without having to pick up your pencil, but it's not differentiable everywhere. Highly obnoxious. Okay. All right, so here's a note about piecewise functions. One of these piecewise functions is differentiable everywhere. One is just continuous everywhere, but not necessarily differentiable everywhere. And one is neither continuous nor differentiable everywhere, and you need to figure out which is which. So I'm going to give you a minute to take a swing at this, and then I'm going to go through the solution on here. Okay. So in order for a function to be continuous everywhere, when you're looking at a piecewise function, each piece has to be continuous, and then the y value at the switchover point has to be the same for both functions, right? So if I look at f of x, let's start with f of x. I know that 2x cubed is continuous everywhere because it's a polynomial. So we know that 2x cubed is continuous everywhere. Same thing for the second piece. That's a parabola. It's going to be continuous everywhere. So we know that both these pieces are continuous everywhere. The only place we need to be worried about where this function may not be continuous is at x equals 1, because that's when the functions are going to switch over, and that's the only place where we might have a gap. So what I'm going to do is I am going to plug in 1 into both pieces and see if I get the same y value out. So 2 times 1 cubed is 2. And then if I plug in 1 into the second equation, you get negative 3/4. Times 1 minus 3 is negative 2 squared plus 5. And you get 4, so you negative 3 plus 5. And you get 2. So you do in fact get the same y value for both. So f of x is definitely continuous. So let's go ahead and check g and h for continuity while we're at it. So again, for g, I see that both pieces here are polynomials. That means they're continuous everywhere except potentially at x equals 1. So let's go ahead and do plug in 1 into both pieces and see what we get. When we plug in 1 here, we get 2. When we plug in 1 here, that's the same as the first one. So we know we're also going to get 2. So this is also continuous. So both f and g of x are continuous everywhere. They're continuous in both pieces because both pieces are continuous everywhere. And then at the switchover point, they also line up so that they are continuous. Spoiler alert, h of x is not going to be continuous. When I plug in 1 here, I get a y value of 1. When I plug in x equals 1 into this equation, you get negative 4 plus 5. Well, I didn't intend for that to happen. Did I do that right? Negative 2 squared is 4. Yep, you also get 1. So this actually is continuous everywhere. Might be. Okay, so now we need to figure out which ones are also differentiable everywhere. So again, for each of them, because all the pieces are polynomials, we know that they are all differentiable everywhere. The only place that we are concerned about is at x equals 1. So to see if it's differentiable, we need to take the derivative of each piece and then see if the derivatives are equal when x equals 1. So in PlayPosit, let's look at f of x. Go ahead and put in what you get for the derivative of the two pieces when x equals 1. And then I'm going to pause this and put the answer up. Okay, so for f of x, I just took the derivative of each piece. I got 6x squared, and then negative 3 halves x minus 3. I just used the chain rule there. Then I plugged in 1. When you plug in 1, you get that f prime of 1 is 6, and f prime of, and the other piece is 3. That's not the same numbers, so you don't get the same slope at the switchover point, so it's not continuous, or not differentiable. I'm going to continue this later.